In this lecture, I'm going to introduce the finite elements in plane elasticity. So let's make a recap of the formulations in finite element analysis using the weak form. So this is the 1D case when we have a bar and every point have one translational degree of freedom. And this will be the case when we have a two-dimensional element. In this case, for example, in this example, I have 4 nodes. Every node has 2 degrees of freedom. That is the x and y translations of the points. So here I'm showing the nodal displacements, and every point will have a field displacement that is going to take a vector in the plane in every point of the element. The balance equations in the 1D case was given by this equation, and in the two-dimensional case can be written in this way. It's a pictorial equation. And the weak form in 1D is given by these equations, and in 2D, so you have to multiply this vector, 2-component vector, by a transpose of vector. So you are going to get a scalar that is related with the weak form. So we integrate by parts in 1D to get the principle of virtual work. And in the same way, we can do this in 3D to get the two-dimensional version of the virtual work principle. In the finite element formulations, we solve the virtual work principle. Written here again. And then we assume a solution as a linear interpolation of the nodes. This is the interpolation functions, but this is a matrix in this case because this is a row vector of all degrees of freedom, and this is going to be a vector with only 2 components, x and y displacements, and this is going to become a matrix. In every element of this matrix, I'm going to have interpolation functions. In the same way, I can have an interpolation of the virtual displacements using the same interpolation functions. So then I can calculate the virtual strains by applying the L operator to the virtual displacements, but this is going to be NE, the displacement, virtual displacement of the nodes, and then I can put these two together, and this new matrix is going to call the B matrix. So the B matrix is L operator multiplied by the matrix of the interpolation functions. The stress is going to be obtained by multiplying the stress strain matrix to the strain. The strain is going to be as the same as this virtual stress is going to be the B matrix multiplied by the nodal displacements. Then we're going to put all these quantities here, replace all these quantities into the weak form, and then we convert these equations into a element matrix equations where this is the stiffness matrix, this is the vector of the external loads, and this is vector with the boundary conditions loads. So how do we calculate the element of the stiffness matrix? So first we need to calculate interpolation functions. Then we calculate the displacement in the field is expressed in terms of the interpolation of the nodal displacements. We calculate the B matrix using this equation, and then we can calculate the stiffness matrix by doing this integral of this matrix, that is the matrix multiplications between the transpose of the B matrix given here, the stress-strain relations, and the B matrix here. So we need to do this integral over a matrix, and this gives us the element stiffness matrix. Let's start with the simplest element, that is a T3 element. This element has 3 nodes, and the displacement is assumed to be a linear interpolation. So here I'm showing the x displacement as a function of xy. It's going to be a surface in 3D. But we are going to assume a linear interpolation, so it means that the displacement in x is going to be a straight surface, a plane in the 3D that is represented by this blue triangle. So the expression for this linear interpolation is going to be like this. It's going to be a three-dimensional plane with some unknown constants, and it can be also expressed as a linear interpolations with the nodal displacements using the interpolation functions. These functions can be found in the chapter 1 of the lecture notes. Here I just write the solutions. So they are given in terms of the coordinates of the nodes and A, that is the area of the triangle. So how to get these interpolation functions? So let's start from the assumption that the u displacement is a linear function in 2 coordinates. So this expression can be written in a matrix format. It's the multiplication of a row matrix of functions and a column matrix with the coefficients of these functions. These functions are called the base function of the elements, base functions. And the row matrix is called the G transpose G matrix, G transpose vector. So if you replace this equation in each node, you are going to get this equation. This is the displacement of first nodes, the displacement of the second nodes, and displacement of the third nodes. And this is going to be called the C matrix. So U is a vector with the displacement, U displacement, or the X displacement of the nodes. A is the coefficients of the base functions, and C is called the C matrix. So now we are introduced the interpolation functions that we wanted to obtain. So they are given by these combinations that can be written also in a vectorial format. This is a row vector with the interpolation functions, and this is the U column matrix. So we are going to combine the second and the third equations. We combine this equation with this one. So basically what we are doing here is we have U equal N transpose of U, but U is equal to CA. So U is going to be, let's start from here. U is going to be these equations. So use these equations. And then A can be obtained from these equations, but by inverting C. A is going to be C minus 1 U. So I have replaced this here. Yes. And then this can be rearranged like this. Okay. So comparing the last two equations, if you compare these equations with these two equations, the second one was obtained from these two, then you can see here we have U, the field displacement in x directions, and here we have here U, this matrix or vector of the nodal displacement in the U directions. You can see that this quantity is going to be equal to this quantity. This gives you an expressions to calculate the interpolation functions. So you just need to multiply the row vector of the base functions by the invert of the C matrix. This matrix can be inverted. In this case, is given by these expressions. In most of the cases, you can invert this matrix. But there are few cases when you cannot invert this matrix. For example, if two nodes are the same, then this row is going to be the same as this row, and the determinant of this matrix is going to be 0. You can also have the case where two nodes are too close to each other, so the matrix have a determinant that is very close to 0, and these calculations of the C matrix is going to give you numerical errors. But in general, if you have three nodes and they are relative well spaced each other, then you can calculate this matrix. So the interpolation functions are calculated by this row vector multiplied by this matrix. So here is the final expression for the interpolation functions. That is the same as the one obtained in the chapter 1 of the lecture notes. So this is the first step. We have the interpolation functions of the T3 element, but now we have to consider the 2 degrees of freedom. So we have x displacement and y displacement in each node. And we can have also two loads, a load applied in x and a load applied in y in each one of the nodes. So here we assume that both displacement can be linear interpolated from the nodal displacement in the respective directions, and then I can write these two expressions like this. So the first equations correspond to this first row multiplied by this column, and the second equations correspond to the second row, this column. So this is the column of all the degrees of freedom of the element, and here this is a column with the 2 degrees of freedom of any displacement inside of the element, and this is written like this. So this is the displacement inside of the element, this is the N matrix, and this is going to be the vector of all degrees of freedoms. So we have the expression for the displacement field, and then we have to calculate the B matrix. So the B matrix is the multiplication of the L matrix by N, E. So the L matrix was given by this is the plane elasticity, and then the N matrix is this one, so we just need to calculate all these operations, taking into account that N1, N2, and N3 was given, and finally we calculate all these operations. So for example, the first component is going to be the derivative of N1 with respect of x, so we have to derive N1 with respect of x, and this gives you this term, and then in the same way we multiply this by this 0, this by this is derivative of N2 with respect of x, that is this one, and this gives us these equations. And then you get this expression for the B matrix. Notice that here for the T3 element the B matrix is constant, it doesn't depend on x. This is going to be important, especially when we calculate the stiffness matrix. The stiffness matrix is going to be calculated like this, but the B matrix is constant. B matrix is constant, so we assume that D, the stress-strain relation, is constant. So this integral is very easy to do because everything is constant, so it's just integral over the volume. That is going to be the area multiplied by the thickness of the element. So remember that this is a B matrix, the D matrix can be expressed in this general form. So this is the general expressions for linear elasticity, plane stress, plane strain, or anisotropic elasticity, and then it's going to give me okay, so the strain can be calculated like this, And at the end, you're going to see that the strain is equal to the B matrix multiplied by the nodal displacement. It means that in this element, the strain is constant inside of the element. So if the stress is constant inside the element, the stress is going to be also constant inside the element. Okay, in summary, for this element, the integrations of these integrations to calculate the stiffness matrix is easy because everything is constant. The stress and the strains are going to be constant along the element. And T appear in the stiffness matrix is going to be unit length if you are doing plane strain analysis, or the thickness of the element if you do plane stress analysis. These coefficients are going to be different for plane stress or plane strain or anisotropic analysis. So we can improve this element and introduce an even better element, that is the quadrilateral element or the rectangular element. This is a rectangle element. Have dimensions A and B, have 4 nodes, and the shape is a rectangle. So in this case, we need 4 shape functions to make the interpolations. So here we need to introduce an extra coefficient because we are going to have 4 equations to solve. So we need an extra coefficient. So to get the extra coefficient, we have to introduce another base functions, that is the xy. So this is a nonlinear contributions to the interpolations. So the interpolation functions are given in chapter 1 of the lecture notes, and these are the interpolation functions. So this is a quadratic functions, and all are in general quadratic functions. And then we can calculate the N matrix by assuming interpolation of the x displacement and the y displacement from the nodes. Here are the displacement in each nodes, and this is the loads applied in each nodes. So the N matrix can be identified here by converting these equations into a matrix equations. This is the displacement in every point, and this is the row vector of the nodal displacements, and you can see that the N matrix is going to be larger than in the previous case. The B matrix can be calculated by doing the same operator, and then the shape functions are given here, so the calculations are a bit more complicated. So the B matrix is given here. So this matrix is not constant anymore from this element. It depends on x and y. And in particularly, since this B matrix is not constant, and the strain is calculated by these equations, you can see that the axial strain in x will change with y, but it is going to be constant in x. And the axial stress in y is going to change with x, but not with y. So the first one is going to be this, the axial stress in x is going to be this multiplied by the nodal displacement, so it depends only on y. And EYY will appear here multiplied by UE, and it's going to depend only on x. So in this new element, in the rectangular element, you are going to see that the strains and then the stresses are going to change inside of the element, a property that the T3 element didn't have. The stiffness matrix needs to be calculated like this. And now it's going to be a bit more complicated to calculate the stiffness matrix because the B matrix depends on x and y. So it needs a little bit more work, but it's possible to do analytically by introducing the stress-strain relations And the final solution is given here. So things are start to becoming complicated here for this rectangular element. But it's still an analytical expressions. So this is the T3 and quadrilateral elements, but we have other elements more sophisticated. For example, we have here the quad 4 element. This is not necessarily a rectangular element, it's a quadrilateral. And you can formulate these elements. This is called isoparametric element. It can be used in cases when you have not straight boundaries, like for example a plate with a hole. You can use these elements to capture better the boundaries. And even you can get even more sophisticated elements, for example this one that has curved boundaries. This size is a quadratic functions and this one is a quadratic functions. These called high order elements. So for example these have 9 nodes, Q9 element, Q9. And they are very good in this case because you can capture better the boundary by quadratic functions. It reduces the error in capturing the boundaries. So these kind of elements, we are going to learn about these elements in the isoparametric formulations of finite elements.